Okay, so this video is about the Brayton cycle, which is to simulate the operation of a modern aircraft engine, which basically is a turbofan. So a turbofan, you have a flow of air that comes to the front of the engine. And then the role of the compressor is to obviously compress or transform all the kinetic energy, the 1/2 mv squared, into very high pressure. So you transform all the energy coming in the flow, you stop it to almost a zero velocity over here. So what's happening is that the pressure inside this section will be extremely high. Now, this is a control volume, and within that control volume at a very high pressure, you're gonna put some fuel or gas and you're going to ignite it. So basically what you have over here is P, high pressure, times a constant volume, PV, plus some internal energy given by the fuel that you ignite will be U. So basically here what you have is U plus PV, and you know that U plus PV basically is the definition of enthalpy. So you have here very high enthalpy, and now the role of the turbine is the opposite than the one of the compressor. It's going to transform all that enthalpy into kinetic energy. So basically the H over here will be transformed into 1/2 mv squared, and that's why the velocity here will be a lot higher than the velocity going inside the engine, and that's how the aircraft is going to fly. Okay, so the cycle that is simulated this is the one that you can see here below. So the compressor simulates this one, then the turbine is simulated over here, and then we have we have two heat exchangers here, Q in, Q out. And that's because we know that any single engine or any single cycle in real life is going to operate between a hot reservoir and a cold reservoir. So you see here, this is Q hot, here will be Q in, and the Q cold over here will be Q out. You see the colors matches. So basically, what we need to find here is the efficiency, and you know the efficiency is always the amount of work produced. So this one produced by the engine, that will be here work of the turbine, divided by the amount of work by the amount of heat that you put in, which will be Q in or Q hot. One thing I need to mention is that really here the total work is the turbine is going to create work, but the compressor, you need work or power to operate it. So generally what happens is that these two are connected by a shaft, and some of the power generated by the turbine is utilized or used to run the compressor. That's why here the total amount of work is work created by the turbine or power created by the turbine minus the power consumed by the compressor divided by the amount of heat transfer you need to put in, Q in this case. So over here, I start just by looking at the system turbine. So basically, you see the turbine create work. So we're just looking at this term over here. And if we neglect any heat exchange with the outside, which is given over here, we find out that the power created by the turbine per unit mass or per mass flow, okay, should be an m dot, is H3 minus H4. So whatever comes in, whatever comes out. Okay, now we do the same thing for the compressor. We need to find the power used by the compressor. So we look here at this page over here, and just exactly now taking the system compressor and neglecting any heat transfer with the surrounding, we have that the power per mass flow created used by the compressor is H1 minus H2. We do the same thing for the heat exchangers. So the Q in, we don't really need the Q out, okay, from the previous equation here. The Q hot over here is the Q in that figure. So we don't really need this one. So we're not going to do the calculation for this one. That's why here I only have the hot heat exchanger, the one at the top, the Q hot between 2 and 3. Again, neglecting any heat transfer between we don't neglect the heat transfer. The amount of heat going in will be by neglecting any work, because this does not require any power or work. We have that the amount of heat transfer coming in per mass flow is equal to H3 minus H2. So at the end, we substitute into this equation, which is the one we had over here, okay? If we substitute directly, we have that the Brayton cycle efficiency is given by H3 minus H4 minus H1 minus H2 divided by H3 minus H2. And this is what is called the Brayton cycle efficiency. And here I'm going to add that in this case, what we're assuming is that everything is being perfect, okay? Next, we can maybe calculate what would not be the ideal Brayton cycle, which will mean what? That we'll have to find we'll have to put into play what will be the isentropic efficiencies of the compressor and the turbine, okay? And maybe one other heat exchanger. But this will be, if you want, like the ideal case. So again, like I mentioned before, in every single time on a Brayton cycle, you have the power generated by the turbine, but a part of the power generated by the turbine is used to run the compressor. And that is what is known as the back work ratio, as I put over here. Typically, a great amount of power generated by the turbine is used to run the compressor and is measured by the work back ratio. So what do you see? What is the back work ratio? Is the amount of power used by the compressor divided by the amount of power that the turbine generates. So if we look at the enthalpies, it's H1 minus H2, H3 minus H4. And here, pay attention that the absolute values is because one of these differences can be negative. And this should be a positive value. Okay, so I'm going to stop this video here describing the Brayton cycle. And on the next video, you will have an example.